and it's taken from the textbook, but it's slightly modified from the example in the textbook. So if you look at 11.7 in your text, you may see something slightly different than what we're going to do here. An automatic opening device for parachutes has stated a mean release time of 10 seconds with a population standard deviation of 3 seconds. So reading again for the 6 items, we have a population mean of 10, a population standard deviation of 3. A local parachute club decides to test the claim that the release time is less than 10 seconds. So this less than 10 seconds gives us the direction and the way we're going to state our alternative hypothesis. The club purchases 36 N, that's the size of the sample, of these devices and finds that the mean release time is 8.5 seconds. So as you read this sentence, you should realize that this 8.5 applies to the mean of the sample 36, not the mean of the population. Okay, just by the context of the sentence, the club purchases 36 of these devices and finds the mean release time is 8.5. So that 8.5 is the sample mean. Does this sample result indicate that the opening device is less than the mean release time of 10 seconds? Use an alpha of 1%. Okay, so this gives us the 6th item that we want to read for. Alpha is 1%. So we start with our null hypothesis. The population mean release time is 10 seconds. Mu is equal to 10. And our alternative hypothesis, the population mean release time is less than 10 seconds. Symbolically, mu less than 10. Okay, so this gives us a hint as to the direction of the test, indicating that we're going to have a test on the left side of the bell curve. The mean of the sampling distribution and its correct symbol, this is where we state mu sub x bar equals, and then we are going to put the value for the population mean, which is 10. So mu sub x bar equals 10, therefore the very center of our bell curve should have a 10 labeled there. Are we basing the test on the normal distribution and the t-distribution, or my? Like before, it's the normal distribution because n is greater than 30, and we have, that should say we have, the population standard deviation. Okay, so let me just correct that. Okay, so it's based on the normal distribution because n is greater than 30 and we have the population standard deviation. Okay, the decision rule. Our alpha in this case is 1%, and because our alternative hypothesis stated less than, we're going to have a test on the left side. We're going to shade in 1% of area in the left tail. That's the alpha. We're going to hope that we get a p-value that's smaller than alpha. If we do, we'll be able to reject the null hypothesis. If we get a p-value that's greater than alpha, we're going to fail to reject the null hypothesis. 10 is in the center. We're going to reject HO at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. So your decision rule is always an attempt to compare your p-value to alpha. You always want your p-value to be smaller than alpha. That will help you to reject the null hypothesis. Now that doesn't matter, well that doesn't change if your test is on the right or the left. You always want your p-value less than alpha to reject the null hypothesis. what changes from decision rule to decision rule in test and in various tests is the value for alpha. Some cases alpha is going to be 1%, in other cases it's going to be 5%. So that's what changes. But you're always going to want P to be less than or equal to the value of alpha. So we're going to go and write down our sample information. The sample statistic is X bar. There is a test coming up where our sample statistic won't be X bar. For example, a sample statistic involving a proportion would be symbolized by P hat. We're going to see that in section 11.2. The value for X bar in this question is 8.5. So if we locate where 8.5 is on the bell curve, on the normal distribution, we know that it's on the left side of 10. We don't know immediately from just graphing this, we don't know how far to the left it is. We just know it's to the left. Once we figure out its p-value, we can then decide whether or not it's very far over or not so far. So when we calculate the p-value, it's going to be the area from negative infinity all the way up to 8.5. So we go to our calculator to figure out the p-value. Stat test z-test. You're going to enter mu sub 0, 10. That's the population mean. Population standard deviation 3. 8.5 is the value for X bar. Sample size is 36. The test is on the left, mu sub 0, so less than mu sub 0. And then you go to calculate and you get your p-value. Rounded to 4 places, your p-value is 0.0013. Also take note here of that z-score, -3. We know that most of the time our z-score is somewhere between -1 and +1. 68% of the time that's going to happen. And 95% of the time we're going to have z-scores between -2 and +2. But here we have a z-score of -3, which is far off to the left, which makes sense when we look at our p-value and it being so small. Okay, so our p-value 0.0013. And then if we look at a visual example of what this means, alpha is 1%, which, this piece of area in my drawing does not look accurate for 1%, but just visualize that alpha is bigger than the p-value. The p-value is the area that goes from negative infinity up until 8.5. 0.0013 is a very small piece of area, so maybe the picture is not too accurate. But you should just recognize that it fits inside alpha. P 0.0013 fits inside 0.01. It's considered very significant. 8.5 is considered very significant because it is less than 1%. Okay, which puts 8.5 far away from center. Far enough away from center to reject the null hypothesis. So the p-value is less than or equal to alpha. If that's the case, then we reject the null hypothesis and accept the alternative. So our conclusion is we reject HO and accept HA at alpha equal 1%. And then we answer the question, does the sample result indicate that the opening device has population mean release time less than 10 seconds? And so the answer here is yes. The sample mean of 8.5 seconds indicates that the population mean release time for the opening device is less than 10 seconds. So the reasoning is this. When you reject the null hypothesis, you reject that the population parameter is 10. Okay, so let's remember that our null hypothesis stated that the population mean was 10. But our conclusion is to reject that null hypothesis, so we are rejecting 10. The established opening time for the parachutes is 10 seconds. Our hypothesis test has shown that this is incorrect. So it's correct to state that the population mean release time is less than 10 seconds. And that is it. 3 hypothesis tests from beginning to end when you have the population standard deviation. So following upcoming tests, we're going to see what happens when you don't have the population standard deviation. Okay, so we're going to use a different type of test in that case. We're also going to take a look at type 1 error and type 2 errors again, because understanding how those errors fit into the hypothesis test is an important feature. So that's coming up next lecture. There is a web work assignment out on this lecture now that you can complete. And if you have any questions, please email me. I'll see you at the next lecture.